PhD in University of Malaya, and the research topic is about technology photonic. So now he is head of Department of Engineering in Faculty of Engineering, University of Malaya. And he will talk about the application of photonic in science engineering. Okay. Please, Professor Sulaiman.
Okay, thank you very much, MC. Okay, so today I will talk about photonics. I think probably now asked me to talk about photonics technology to give some idea. Actually, it is a multidisciplinary field. Actually, photonics is anything related to the light. I think most of you do research use light as a tool. Okay, so I put as title photonic the technology that is coming at us with the speed of light. Okay, so I will talk about the history of the photonic innovations. What is light? About laser and optical fiber. And then maybe about the photonics, the fiber, microfibers, laser applications, or some work in the photonics. Okay, everything started in 1,000 years ago. The first book of optics, written by Al-Hazir in year 1015. So whatever we learn in school, reflection about light is actually from this book. So it's not the new technology, it's 1,000 years ago by Al-Hazir. To celebrate this, to remember this, 2015, so UNESCO declared International Year of Light. So we have International Year of Light 2015, and why I tell this, I think Al-Hazir is actually a great scientist. They are from Baghdad, moved to Egypt to solve the problem in Egypt. So he cannot solve the problem, he was jailed. So he wrote this kitab inside the prison. Okay, so inside the prison, what they have? Light and dark and light. Maybe, yeah. So they have nothing, yeah. So with nothing, they managed to write the book, no. So the take home from this story is actually you can do science. If you don't have any equipment, you don't need to worry. You still can do science. You can learn science. Yeah? It depends on you. It's not depend on the equipment. It's not depend on where you are. You can be in prison. Can do great science, yeah? And people, follow you until 1,000 years. Huh? And then the first photonic revolution actually started in 1960 because of the inventions of the laser. It's not invention. Actually, the idea of the laser 50 years ago, 1916 by Albert Einstein. If you still remember that they talk about the stimulated emission on light generation. So people know we can generate light, but nobody demonstrated all theory. Yeah? So the first demonstration in 1960 by the Tido Maiman, the ruby laser actually. So they generate ruby laser. Ruby laser is red in color. Why? Because they have a chromium ion. So the chromium ion actually is come from the chromium. Material is chromium. So chromium absorb the visible light there. This green and blue, they absorb and get emission in 694.3 nanometers. Use the visible light come from the flashlight. Because in 1960 the camera was there. Camera used a flashlight. So they use whatever they have. So they demonstrate the first laser 16 May. To remember this, UNESCO declared International Day of Light. So every year, 16 May, we celebrate International Day of Light to remember the first demonstrations of the laser. But Tido Manga wrote paper on this inventions. So they write paper, sent to journal, he got rejected. He got rejected, the paper, even though the first revolutions of the photonic, because during that time people cannot accept their idea, so the paper was rejected. So you don't need to worry if your paper got rejected, because Hidup Mama also paper got rejected. Okay? And the discovery of laser has led to the tremendous benefit of society. For example, telecommunication, so we can have fast internet because of the inventions of the laser. Okay, because laser is important as a light source. And energy, for example, in solar cell, some people you do the solar cell. Solar cell is conversions of the light or heat to the energy. So in medical, medical now so advanced medical photonic technology, there is imaging technology. It's come from the light lens optics. So when we can capture a good image, so we understand better. So the medical here good because of they can clearly see what inside. Okay, and many other fields. And in future they have a fusion energies here to replace the sun. To combine the atom, nuclear combine, split the atom, that is more dangerous. So the new energy source will be not split but combine ion. So the atom and this ion is come from the source is seawater. That is abundant, so they can generate a lot of energy, but they require high power laser. So they require high power laser to make that happen. So I think they made the first reactor to fusion energy. Actually, they under construction in Europe. Okay, it's successful. So maybe this the important source of energy. Okay, and future. Now you use Wi-Fi. Wi-Fi is today's standard, maybe slow. You want very fast internet, fast communication. Okay, Wi-Fi is 100 times. So they can give 100 times faster. Wi-Fi, everything optical. So now from the, it's not all opticals. It's not come to our laptop, our phone. It's all wireless. It's wireless, but it's not optical. They convert to the electrical signal. So if you put all the optical using LED, because LED you can model it. Okay, as a source. So Wi-Fi can give the speed of maybe 100 times faster. So this near future. So in manufacturing, or cutting, welding, or now people do laser, high power laser. Okay, yes, and also in medical applications. So photonic is actually a branch of optics that study the method of controlling the propagations of photons that make up the light. Actually, we control the photons. We study how to generate photons, how to detect, how to manipulate, how to rotate, whatever. Okay, so this is a photonic technology. And light, what is light? Okay, light is a kind of energy. We know the light is electromagnetic wave. It's actually a wave and also photons, particles. Okay, so certain as phenomena like this diffraction, we can split the white color into separate color. We can split the wavelengths of the light using prism. So this can be explained if we consider light as a wave. Okay, optical amplification, for example, how we amplify the light, how we generate light. We need to explain, we need to consider the light as a photon. So light have the duality characteristic as a photon, as a wave. So they have both characteristics. Okay, light can interact with the material and structures. So light, they have energy, photon energy, hc over lambda here. These are photon energy. And you see that h is a Planck constant. C also constant. The only variable there is actually lambda, wavelength. Wavelengths of the light. So actually photon energy is dependent on the wavelength. Okay, so we can say that photon is actually a wavelength. So wavelength, what is wavelength? Do you have any idea what is wavelength? What is wavelength? Wavelength is a color. Different color, different wavelength. Okay? 400 nanometer blue. 550 is green. 600 so red. But you see red, a lot of red. You know, maybe women know when you buy something, they have a lot of red. Because 600, 610, 620, 620, so different color. We generalize as a red, but different color because different wavelength. Okay, so this actually, the color is wavelength is actually colors. So you can split here, we split wavelengths here. So you see in color because the visible range is only 400 to 700 visible wavelength. 400 to 700. So we have color that we cannot see. Like communication, we use 1.5 micron. 1.5, of course, we cannot see 1.5 micron. Infrared. UV less than 400, so we cannot see also. And dangerous. UV dangerous because the shorter the wavelength here, UV, because the wavelength is short, so the energy is high. Okay, so the photon energy is high. If our skin absorb the UV, so you become darker. It's because of UV. This one thing. So another thing, UV, they can vibrate your molecule. The molecule tissue, so they can vibrate. Vibration, they can generate. If we vibrate, they will generate sound. Okay, the vibration, so they generate sound. Phonon, we call phonon. Okay, they generate sound. Phonon. So phonon interaction with light and phonon can generate something. So vibration can cause the damage of the DNA. Okay, it's vibrations. That's why UV can cause the cancer. Okay, like anything, your phone, if you put vibration, only vibrate, so they easy to damage, right? Like our body, the same thing. We cannot vibrate so much, so they can cause cancer. So UV dangerous. When you work with UV, be careful. They can cause you skin cancer. Okay. So lasers. So laser, we talk about laser. Laser is, in principle, is based on the stimulated emission process. So laser, you need to have material. This element of the laser, they have a active medium. So like just now I said ruby laser, they have chromium ion. Chromium is actually a medium, material. And you need to pump, to put some energy here. And then you need to have resonators here. The light go forth and come back here because the light will be amplified many times. You need to amplify many times so that you can accumulate the energy, intensity of the light. You can multiply the number of photons. So intensity of light depends on the number of photons. So you can multiply by the process of stimulated emission. This Albert Einstein that found a stimulated emission. Right? So you have one photon, they can generate two identical photons. if the band gap of the materials, so whatever active medium that you use here, so they have band gap. I think you know band gap. So energy band gap. So if the band gap is equivalent with the incoming photon, so the material will be absorbed. So transparent there, you see the glass transparent because no absorption. So there is the band gap of this glass is not fall within the visible range. So you can see how transparent. So if band gap equal to the incoming photon, they will generate two identical photons. Two will generate four. This multiplication, that's why we multiply the number of photons. 2 become 4, 4 become 8, 8 become 16, become millions. So the higher intensity means the higher number of photons. So when you pump here, you can generate photon. Photon go here, they coming back here, they get amplified. Go here, coming back, amplify many times. Many is maybe million times. It's not 1, 2 times. Until they're saturated, so they can emit laser. So you can get high density of light here. So because they are identical, the photon is identical. Identical means they have the same wavelength, the same colors. They produce the photon with the same colors, with same direction. That's why laser, they have directions. The same direction and the same phase. The same phase, so they are coherent. That's why laser very important in that's why we can use for many, like in industries, photolithography for example. Because to get interference, you need laser light. You need coherent light source. So in camera system, so we also need coherent light source. So this is important, coherent. So laser diode, I think laser diode is invented in 1962. So laser diode, what is laser diode? Laser diode that we use is come from LED, the same thing. LED is not laser, so they don't have mirrors. So they only come out one. They not amplify many times. Laser means they have mirrors. Okay, so they have like resonators, mirror that can amplify many times. So the same principle, how they generate light, you have semiconductor, P-type materials and N-type materials. It's quite easy. You just leave N-type material, make thin film, you make P-type, N-type and P-type together. You provide current field, forward bias. You provide current, you get light. Come on, right? Okay, so you get light. So just a PN junction. So that's why LED is very cheap. So the problem with electrical engineer, so we to invent this thing is quite difficult. You know, semiconductors or whatever. But when you produce the first product, it costs a lot. But after 10 years or after a few years, the price dropped to zero. You know, LED now very cheap, you can buy. Yeah, because it's nothing. It's 2 layers of materials only. It's nothing in terms of. But to develop is quite difficult. So chemistry is better. If you develop a cosmetic, for example, the price never change. The price of cosmetic never change. But handphone will change. Okay, so now, yeah, maybe, you know, this handphone, another 5 years, maybe very cheap. No? All people don't use handphone anymore. Okay, the technology very fast. So you need to get your money back fast. But this actually the first laser diode is not efficient. In 1970, you get very efficient laser, right? Because they introduced the heterojunction. Okay, so this laser diode and this UV. Now people work on the UV. Okay, UV range. because UV they cannot produce by solid state. Very difficult. Now, a lot of research on that. They are used widely. You go or industry, you do the fabrication of the electrical component, chip, all these things is used. Use interference. Lithography is used UV. But UV normally we use the gas laser. So gas, the problem with gas, like our aircon, after 1 year is leaking. Gas tend to leak. So people work very hard to get in using the semiconductor, for example, solid state. So a lot of work on this. So hot topic to reduce, maybe to get to 74. They can get like UV. They call UV about 400. 400 is not UV actually. It's not really UV. But people say UV. If you purchase UV, actually it's 400 nanometer. 400 nanometer is visible range already. It's not UV. Okay. Second photonic revolution is optical fiber communications. Okay. We use optical fiber as a transmission medium by making the core effective index larger than the cladding, so you can guide light inside the core. Okay, so you send them this whatever we write here or picture, actually we convert to the digital signal. Actually, it's convert to the digital signal by our computer. 0101, this digital signal. So in the how we do communication, actually we have transmitter here. We have laser, and we modulate the laser according to the digital signal, and then we send the modulated signal. Okay, so actually they can carry a lot of channels here. Okay, a lot of channels. Okay, so many channels. Actually, optical fiber, even though the core size is about 9 micron, but we use light. Actually, the advantage you can put many channels, mean different wavelength. You can propagate different wavelength inside the core of the fiber, so they can increase the capacity. Okay, but of course, the Moore's law, if you Moore's law, your capacity is doubling every 2 years. Every year they increase, but they double. Whatever capacity that we need today, after 2 years will be double. So engineer need to work harder, because the demand of the capacity is doubling every 2 years. So, but this low loss region for the optical fiber is only 100 nanometers. So we need to expand this, so the new technology is come up. So this is about optical fiber. Actually, optical fiber, the idea for optical fiber by Charles Cow, that gave the idea to use for communications in 1966. So he got Nobel Prize in 2009. He passed away in 2010, 1 year later. So he demonstrated the first optical fiber. They have 20 dB loss per kilometer, mean 99% of the light loss. But they can reduce after a few years, because glass is old technology, it's not new. Glass, if you go to Egypt and you see the ceramic, you see the museum, during Peran, they still have, they got glass already, beautiful glass technology. So this technology is 6,000 years ago. So it's not big deal. So very fast they can reduce the loss. This optical fiber, actually, they can carry a lot of information. Actually, the greatest optical gift to the mankind. Why? Because it's made from the silica, from the same abundant materials. Okay, and then the price now is cheaper than spaghetti, of course. So much cheaper. You can buy one, maybe I think it's almost free. Okay, now it's almost free. Optical fiber is actually almost free. It's not expensive, unless for the special optical fibers. If you buy 10 ringgit, 20 ringgit, it's actually free. And this optical amplifier, the inventor to amplify. So we have these three guys that introduced optical amplifier. This David Payne, Gills, and Emmanuel Disselway. Actually, these three guys. Okay, that proposed erbium dot fiber amplifier. So you have optical fiber, they do with the erbium ion. So they can amplify at 1.5 microns, the wavelength that we use for communications. Okay, and then this photonic crystal fiber is the new technology. So we can make optical fiber, they have many holes. Okay, these two guys introduced by the Philip Rusher and Jonathan Knight. So they first introduced this fiber actually because of the demand of capacity. So optical fiber, they have one core. Okay, so now they want to increase. So one optical fiber, they can have four, for example. Four modes. Four modes in one optical fiber. Because if normal fiber, you cannot control the number of modes. If many more, it's very difficult to control. So they can restrict to 4. Okay. And another advantage here, normally in normal optical fiber, you need to have core refractive index larger than the clarity. Light travel faster in the vacuum actually. Because vacuum or air here, we have the lower refractive index. So if we can send the light through the air here, okay, so this air transmission so can be faster. Okay, so we can make air as using the photonic band gap effects here. Okay, so this the technology for we call microstructure optical fibers. So they may have a lot of applications and features. Okay. People do, but people will think how to use all these things. And we can generate a supercontinuum light source. If we have photonic crystal fiber, here highly nonlinear optical fibers. Okay, you have the pulse laser. You inject here. You can create the broadband light source like coherent and broadband light source. This is very important in the OCT application. This OCT application. So you want to get image. Okay. How to get image? You need to have very high intensity, because if you use maybe photoluminescent, they're not really high intensity. But a supercontinuum is better light source, so you can shine light into specimen here, get the image here. So through the image processing, you can get the very good OCT system, OCT scan. Okay, so we know optical fiber, they have 125 microns diameters. The core size is only 9 microns big. Because now we talk about nanotechnology. So some of you working in nanotechnology, we talk about the nano. Okay, over the past 40 years, optical fiber have been finding successful application, communication, sensing, fiber lasers, and nonlinear fiber optics. So we have done a lot of applications. So there can be linear optics, light transmission, and then nonlinear optics also. I show you for continent generation just now. It's based on the nonlinear phenomena. Nonlinear phenomena inside the glass. So you can generate this supercontinent light source. Okay, so this normal optical fiber. What happens if we reduce the size? Okay, it's very interesting if you reduce the size of optical fiber from 125 micron to the maybe 1 micron, or even in the nanoscale.
what happens? Miniaturizations of optical fiber. The motivation because of everything, because nanotechnology, we know we make the thing smaller, we can increase the sensitivity of the device. So the device will have the faster response, higher density. Yeah? So you can put, for some application we need to put to our body, for example. You make laser, small laser, so that laser you want to put it in your body. So you must be very small, micro scale, nanoscale. And we know in electrical engineering, we use wire to transfer electrons. Okay, current you can transfer copper wire, touch another copper wire. You can transfer, but light you cannot transfer like that, right? Light, optical fiber inside the core, you need to align. The core should be aligned so that you can transfer to another device. Okay, and okay, so it's quite complicated for the light to be transferred. So this is a question. The electromagnetic wave can the photon in the glass fiber behave like the electron in the copper wire? So we have that question. Okay, we can making connection by a simple touch. Whether we can do that or and optical fiber, we know they carry light. So beside light, can they carry other things? Like nanoparticles, for example. Whether they can carry or not. So the answer is yes. We can do that, provided the fiber is thin enough. If reduce the size of optical fiber comparable to the wavelength of the light, for example, wavelength 1.5 microns. So if the size also 1.5 micron, so we can do this thing, or smaller, even in the nano size. That's what we call microfiber or nanofibers. So this, if we use this, we can have this. Okay. Okay. So these normal fibers. Okay, 1 to 5 microns, the glass. You can reduce the size. 150 nanometer, for example. This our hair size is maybe 100 micron or 50 to 100 microns. So you can make smaller. If you can make optical fiber small like this, it's 700 nanometers. You can make that. So this nanofiber or microfiber, depending on the term we use. Okay, we can do that. Okay, optical fiber or microfiber is optical fiber with diameter close or thinner than the wavelength of the light. So we can make that device. What happens? They will change the characteristics. Okay, first single mode guidance. Okay, we know in the communication we use these normal fibers. If you shoot the broadband light source here, what you see here, so here we operate at 1.5, mean at 1.5 is single mode. So for the communication, the optical fiber we carry one mode, single mode, because easy to control. One mode is no dispersion, easy to control. Single mode. That's why whatever application device you use single mode, but you don't use visible range, infrared, because they have cut off wavelength. Your fiber here is multi-mode. Only at wavelength infrared they have single mode. So by microfiber you can make this part is single mode. If you reduce the size to 1 micron here, you see overlap here. Okay, so here is a single mode. Okay, single mode in the visible range. Visible is very important because you don't appreciate it. You cannot see. Only if you do experiment, if you cannot see infrared, it's not interesting. People, you cannot make people happy if not invisible. Okay, So this one advantage. And the second, low optical propagation loss. You see the loss, even though you reduce size 1 micrometer, the loss is very small. Overlap here means the loss is unchanged. So low loss optical fibers, less 0.1 dB per mm actually, typical. Very small, 0.1 dB. So you can transfer energy from the normal fiber. If you have 10 milliwatt, for example, light, you can transfer to the nano fiber, maybe 100 nanometer of diameter of the fiber. You can transfer the same energy. So 10 milliwatt can do a lot of things there. They can be power density very high, and they can vibrate the molecule, can generate nonlinear infection. They can generate a lot of phenomena, a lot of science you can study there. Okay, you can transfer light because if you do in the big system, it require maybe kilowatts of the power that we don't have. But if you reduce the size into nano, okay, so you require lower power for demonstrate. Okay, so this microfiber, actually light is propagate outside mostly. It's electric field actually, electromagnetic field. It's actually light, it's like a field. It's guided by this, but actually most of the field outside actually. It's not in the fiber, but it's outside. Okay. If we have the small fibers here, small core, so high fractions of the evanescent field is outside. So they can cause the two effects. First, they have larger optical gradient force because light, they have the force, they have a force that you can use this force to move atom, to move bacteria, to move virus. For the medical application, you can move all this. Or normally people, atom trapping, for example, you can use laser light. Normally people use laser light as optical tweezer, optical tweezer. So you shine light to the virus, for example. So virus cannot move because of this gradient force. So you can remove other part except the virus. So this is very important for you to to remove the bacteria, to manipulate all these things. You can use light power. So the gradient force from the light. So this atom trapping and waveguiding. So we can use for this application. And they have a stronger near-field interaction because all the light traveling outside. So it's very good for sensing. Very high sensitivity optical sensing because they can interact. If you want to detect gas, the light will interact with the gas outside because it's propagating outside the fibers. Mostly 80% or 90% of the light traveling outside. So you can use for optical sensing. Okay, as I said, because you are small just now, so the power density, even you launch 10 milliwatt, because of power density is high, they can generate supercontinuum light source. This supercontinuum light source. So this we can demonstrate supercontinuum light source. They can generate supercontinuum light source, mean broadband light source, because of the nonlinear effects. In study physics, because many Raman scattering, forward missing effect, SPM, self phase modulations. Okay, so they can cause the broadening. You get broad. Okay, so conventionally now people use photonic crystal fiber, the fiber to generate supercontinuum light source. But photonic crystal fiber expensive, very expensive to make the microstructure of this, very expensive. But this very cheap. Okay. Okay. Another, they have strong evanescent coupling because most of light traveling outside, so you can transfer light from this microfiber to another microfiber. You just touch, all the light field will transfer to another waveguide. So to transfer light from waveguide to another waveguide very easy, just by touching something. Okay, so this I said, you can touch, it's like copper wire. But must be small. They have a large waveguide dispersion, because most light traveling is outside of the core, so they have the negative dispersion. Large waveguide dispersion can be used for optical the dispersion compensation for the communications to make the device. Okay, so why this very important? Because we can make microfiber, nanofiber is cheap, very easy. This fabrication. We need to have heat on it. Flame, we use flame, or you can use laser, CO2, or you can use electrical heater. But laser is better control of the heat. You can reduce size smaller, but more complicated, a little bit complicated. Electrical heater also, because you need to use high current. High current, so heater can be very expensive. It's too expensive, but this flame is easy. We use flame. Okay, to make microfiber. This is what we designed in our lab. So we can make 1.7 micron, for example, this. So the raw material is fibers, For this research is very, very, very cheap because you use fiber. Optical fiber is, I can purchase 1,000 ringgit, maybe 3 juta for 25 kilometers. 25 kilometer length of the fiber, so I can use until my grandson die. Not never finish, working every day, never finish. And flame very cheap. We use butane cooking oxy butane flame to heat. We need to have small nozzle here. This nozzle that we use to kamas pakai. So they have small nozzle there. So we can make this microfibers. So we can make a lot of devices here. This ring resonator, we have Mach-Zehnder parameters. So we can make many structure devices. We can study. So, okay. So this, for example, you have the ring structures like this. We call micro knot resonator. So if you change diameter here, so the pattern here will change. And they react with the temperatures. So we can use for high temperature sensing. So the shift of the wavelength here 50 picometer per degree Celsius. So they have a lot of this application, this Mach-Zehnder interferometers. So this optical component, maybe you're not familiar. So we can use for current sensor, the flow currents here. Many things we can use. Temperature sensor, because the idea temperature sensor for high temperature. For low temperature, I think you can use conventional sensor, but for high temperature, silica have the melting temperature is 1200 degrees Celsius. So we demonstrate until 800 degrees Celsius, a linear relation. So you can make the probe of the sensor very cheap from the microfibers. Strain sensor, even small nano size, but they are very robust. They're very good for the strain. Strain measurement. And this we can cook something. This we do something on the zinc oxide coating. Okay, you can cook to the fiber, to the microfiber here. For this, for example, uric acid sensing. So we cook to the microfiber to fibers. You can put your nanorod, zinc oxide nanorod that using the hydrothermal process. Hydrothermal process is and this one we do with the agaros. You put agaros for humidity sensing. We make we put this the dye. You can make the small lasers, size 400 micron laser, small lasers. Okay. You put this zinc oxide nanowire. You attach to this structure, so we can generate the UV, because zinc oxide can be used to generate UV light. So this people have demonstrated for UV laser. Okay, so motivation for working for microfiber. So they have this characteristic. So they create a new opportunity for photonics. Okay, so they have lot of application, unexplored application that we can explore. So these the applications we can use in microcavity, optical sensing, quantum and atom optics, non-linear like we for continuous light source, plasmonic, optomechanics, lot of application. So these are some work about the whispering gallery mode for sensing. So we have microfiber here. We make this bottle structure. This structure, this normal optical fiber, they have cylindrical. And then we use a fusion splicer. So you make these dumbbell structures here. So you can put here, you can get this mode, this whispering gallery mode that we can use for various sensing applications. Okay, this plasmonic, you put some metal, the interaction between electron and photons can produce the plasmonic oscillations. Plasmonic oscillation. Okay. Normally people use this prism. So when you shoot light here, you get this evanescent field. If you have the gold layers here, metal layers, must be transparent. Gold should be very 40 nanometer, 50 nanometer. So the gold is actually transparent. If 50 nano is transparent. You coating there, I think this Prof is doing in the lab this plasmonic. Okay, so you can get, you change the angle here, okay, you get the resonant wavelength here. The resonant wavelength depend on the surroundings here. So you can use the angle we change depend on the what happened here, refractive index of surrounding. So you can put functional coatings here for biosensing. Normally people use plasmonic for biosensing because whatever you want to sense, virus, whatever, we react with this material, we change the property. So the change of the property you can see from the change of plasmonic resonance angles. Okay, so this is example of biosensor, plasmonic based portable biosensors. Okay, fiber lasers. Okay, kita ada masa lagi. Sikit lagi. Berapa lagi ada?
Yeah, 5 minutes.
5 minutes. Okay, so I just fastly go through lah. We can make laser, fiber laser that depend on the material. Which material we can get at different wavelength region. Normally, for medical application, people want at the 3 microns. This laser, so this we can use nanomaterials. This we put inside the cavities here. We make fillers, so we can make the pulse laser. This our pulse laser. We put this the laser cavity, ring cavities, and then you see here a lot of you can get the pulse here, 152 femtoseconds laser using the fiber laser. So if you see in the wavelength domain like this time domain, this frequency domain, so this also smaller time domain. So you measure the pulse duration. Okay. So we use various nanomaterials here as optical component to modulate the laser cavity to generate pulse. Okay, this pulse laser has many applications in nanosurgery, in microscope, in spectroscopy, okay, in communications. It's a lot of application, and high power. So just now is ultra short pulse laser. You can make high power laser, but different structure. High power, they have different structures, so we need to combine many pumps here. This pump laser combine, and then you get a laser. This high power. This the structures. So high power laser has many applications. Okay, drilling. So, but the most important application is actually in a weapon system. So normally, so this the ultimate goal actually to use as a weapon. Okay, you can use also light photon for agriculture. Because if you put the certain wavelength, because they put on, I think the purple colors, I think these 390 something colors, actually they can make the photosensitive activity better. So it's good for the plant. So you can do 24 hours. So this for agriculture, can use also for agriculture. Okay, we have welding. This we use our high power laser. We can weld. Very easy now. It's not in those. Our high power laser. This laser to weld. Okay, no more easy to do. This laser welding that we have done in our lab, and we also can use laser for in industry soldering. Okay, so you can use laser soldering system. Okay. So as a conclusion, actually, the demonstration of the first laser has created the revolutions of the photonic field and has changed the world. Actually, photonic is a key enabling technology for various industries. Okay, I think that's all. Thank you very much for your attention.
Thank you very much, Prof. Sulaiman, for fascinating talk. Okay. Now it's time for discussion. Any questions? Okay, please. Yeah.
Okay.
Maybe you can introduce yourself first.
Yeah. My name is Ashikale Samjami. I'm lecturer in robotics and AI engineering, and my current research is actually as intersection with communications. So what I want to ask is about communication.
Yes.
We rarely use optics or lights to transmit data transmissions because it costs expensive actually. Yeah, because we have fiber optics, and compared with the LAN and wireless, where we use electromagnetic, is more cheap, more expensive, right? And my question is, actually, I'm quite interested with the information about the Wi-Fi. Yeah, because we don't use fiber optics. Yeah. My question is, in electromagnetic, we sometimes deal with the attenuations, distortions, and interference. Are you deal with this kind of problems in the Wi-Fi or something else?
Okay. So because you from outside, you see everything while you use phone actually. You send message, actually you use optic. It's not actually from here to they call the station only the wireless. Near maybe 1 kilometer you go wireless. And then after that station, they must travel. You send message, they must go to server. Server located in Silicon Valley, Google. So whatever you message, we go to Silicon Valley and come back. You message your friend there, come back to your friend there. So they travel. The light travel actually 1,000 kilometers, 10,000 kilometers they travel, and they very fast because light travel very fast. Actually, everything is optical. Wireless is here to the apa dia panggil the station. But actually, the loss of light, I think, because free space they have more loss. Free space is more loss. Inside the glass is we can control easily. So all inside the optical fiber. But for free space, I think free space is because Wi-Fi it will come soon. It's not it's like electric car, the same. They will start anytime. Maybe 1-2 years as we have Wi-Fi, and then because now the problem because we use electronic also the same wireless system, microwave. So just different wavelengths only. Actually, the system is the same. Actually, the system is same. It's the microwave is different wavelength, different frequency. That in terms of modulation, the light modulation is easier. Actually, that's why people use your free space optics. You see, you go Korea, for example, there are a lot of people do the free space because free space is good in town from building to the building. If you want to send the communication very easy because so I think it's not really a problem actually to convert everything to the optical domain. Actually, the same system, just optical domain. Wireless mean optical domain is 1.5. You microwave maybe at the longer wavelength. At the longer wavelength. So I think should be near futures lah. Should be. These both are photonic. Even you go microwave. Microwave is also actually the same. It's also photonics. Yeah. Wireless is also photonic because different electromagnetic wave. Yeah? Everything is magnetic wave. Just to change the region to the this optical. We call optical. This mean in 1.5 region.
So in the optical, we also know that have a frequency and amplitude and like the phase in.
Yeah, the same. The same. Because they want to go on the visible range. For Wi-Fi will be visible because they need to use the same light bulb. Okay, but they modulate because modulation is very fast. You cannot see. You see, it's the same because modulation is very fast. So when they change to LED, everything LED. So, but they need to change the device lah. Because to introduce the new one is quite complicated actually. We used to use this. For example, in those days, when I work in company, in those days when I work in industry, actually my company making the this for monitor they use CRT tube. We make the components. So people say next year nobody use, everybody should use flat screen. Actually, to change to the flat screen is, I think, more than 10 years. Even the flat screen technology already matured, but still people convenient with this CRT. But now, of course, nobody uses CRT anymore. but it's not easy. The same thing people use with wireless. But that one also wireless lah, but in the okay. Any other question?
Any other question? Yes.
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 Professor, the fiber is made from silica.
Yes.
Is it possible if inside of the fiber there are some dislocation, for example, like oxygen vacancy or some microstructure or nanostructure dislocation? Is it will change the transmission of light? So is it possible for that? And then can we control by using the defect of the you saw us that we can control the light with the design of the fiber, right? Like
Okay, this is a photonic crystal fiber.
yeah. Is it possible if we also can control it with the, for example, defect from the silicon dioxide?
Fiber that transmission fiber, actually transmission fiber that people use, that very cheap, I say very cheap, is already matured in silica, because silica they have the low loss at 1.5. It must be pure silica.
The pure.
But they can, last time they have absorption loss, but now they manage to remove the water. So they are already matured technology. Another application of the fiber is to make device. Like photonic crystal fiber, maybe they have hollow core. So you can put in gas inside the where they put gas. So they can do the gas laser, for example. So they can put gas as medium, like we have laser. So they can put gas there. So they can manipulate the hole. Actually, you can block light by, they have many holes. Photonic is the fiber. You see, photonic is the fiber. So they have many holes here. These structures. So people design very structures. So they have the photonic band gap effect. Means you can control the transmissions of light depend on this the distance between this hole and this hole. Okay, so they can control, they can block. So you can do switch. If sometimes the hole you can control by heat, for example, by heating. You put temperature high, so they can block the light. So they can increase the hole certain level, the distance, so they can block the light. So they can do the. So that's how we manipulate light. We stop light, so we switch. That's why we make the devices, photonic devices.
I see. Oh, so yeah, I forgot. So this is basically different with the electron transfer, right? So that seems like the defect should be not quite much effect to the light transfer, I think.
Defect of
The defect of silicon dioxide, for example, like not the whole, but
the defect of
for example, like I'm sorry, in this one, and this is silicon dioxide, right? If we put some oxygen vacancy, for example, so is it will affect to the light transfer?
no,
I think should be not, right?
No, because if we have some, because we want the structure to be transparent.
I see.
If you have defect, you get certain band gap here.
I see.
That band gap can cause the absorption.
I see.
So they can absorb the light, so they can give the loss.
I see. So that's why you say that the silicon dioxide should be pure, right?
Yeah,
That should be pure, and then
silicon.
yeah, I see. Okay. And the second question is about the laser, and I think you know about the pulse laser deposition to make
Laser, yes.
to make a thin film.
Thank you, yeah.
Actually, in my PhD I did that, but unfortunately when I came here we don't have the equipment, and then the problem is also related to the KRF laser. It should be very expensive.
Yeah,
think
krypton. And how about this one?
That one UV. I think
What kind of laser is?
no, that one you want to do ablation.
Yes.
Ablation. Normally people make the thin filler.
Yes.
Using, I think my colleague in UTM, I think what they did actually you can purchase laser very cheap. Now the high power laser, you buy the laser for in eBay they have lot for skin treatments. They have a Q-switch laser that selling online. You can buy online, maybe 500 ringgit.
Oh, they use that laser.
Is it the same
They are the
laser
same.
Really?
for removing the hair?
Removing the
But the
hair,
power is not to.
tattoo removal,
I see.
or that laser.
I see.
You can purchase from China.
Okay.
Sometimes it's quite powerful.
I see. How much the power if you know the power of the laser?
The power sometimes they claim lower but actually high.
Is
Okay.
it not dangerous?
Huh?
Is it not dangerous?
You need to handle carefully.
How about this the laser you show me? You show us about
The one
Welding we use
Welding.
this semiconductor laser.
I see. So is it possible to be the laser for
It must
laser
be high
ablation?
power. They need to have pulse
Yes.
Fast.
Okay.
and high power.
Mm-hmm.
That one.
Yes.
And you can use for ablation.
I
You
see.
can modify this. You can buy from, I think they go China or online. Alibaba. They sell a lot. Even Shopee also go.
I
You
see.
can buy, you can modify. That one is quite high, so you just shoot to the metal, vibrate, so you put your sample. You can try,
I see.
Uh,
Because last time when I was went to Japan 2 weeks ago, my advisor already changed. They did not use. They don't use the krypton anymore. When they use another kind of laser, but I forgot what kind of laser. It's because the KRF is very expensive.
Krypton to one excimer laser.
Excimer laser.
Excimer laser is UV laser.
UV laser.
UV laser expensive
Yes, very expensive.
because it's gas laser.
Gas laser. That's
You need to use solid state. But
Solid
I
state.
don't know, depends. Certain material they need UV. I think why they need UV, I'm not sure.
Mm.
But this one in the visible range, in the other range of wavelength, krypton in the UV range. So UV, people make normally krypton use to make the fiber grating. Grating to make the photolithography. People use all that. They want to make the permanent damage on the materials to make the structure.
Thank you.
Any other question? Yes, please.
So I have a question. I am actually my focus and my user focus is on robotics. Because now I think I believe in the future, fiber optics will be used as communication devices that will be used to transmit the data between so many actuators and sensors. But as you know that in the robotics there are so many joints, so it will make the optical fiber becomes twisted or bent or something like that. Is there any like the maximum bending angle or the twisting angle for the optical fiber?
Okay, actually optical fiber can be bent. Normal fiber you can bend, cannot be smaller than your finger. You can bend normal fiber you can bend. There is no problem. And of course for the advantage of optical sensor, why people use optical sensor? People don't use electrical. And because electrical sensor, if you have 10 pieces of sensor, okay, probe, you want to measure at one point, okay, you can use normal. But if you want to measure not only one point, maybe 1,000 points, so you need to optical. Because optical, you can combine the signal. You have multiplexing. So like in the driverless car, or the optical sensor there, because you need to send at the many point. So it's impractical in the electrical. data processing very difficult. So optical, so you can split the light, you can combine, you can split, so you can get all the information for maybe thousand point, maybe million. If you have million point that you want to measure things, so of course you need to use optical. It's impossible you use very. I think you cannot do electrical. You cannot multiplex. You cannot get data simultaneously, real time, for so many points. Okay. Any other question?
Students, maybe? No? Okay, maybe this is the end of our talk.
Okay, thank you very much.
Thank you very much. Yeah.
For your attendance, question, everything. So we open for collaboration. You can contact me anytime for any collaboration. If not with me, with my other colleague, UN, I head of department of electrical. We have many other people that do different type of research. Okay.
Thank you.
Very much. Yeah, before we finish the discussion, maybe we need to take a picture together.
Okay.
Maybe with the title in the front.
Okay. Saya dipilih.
Rapat. Miring.
Boleh nampak.
Barangkali bisa kita nata, Mas. Kita nata dulu. Mas, kita nata dulu gimana?
Nggak apa-apa.
Kelihatan semua nggak?
Kelihatan semua.
Kelihatan. Oke.
1, 2, 3. 1, 2, 3. Cheese.
Okay, thank you.
Thank you very much,
Okay, thank you.
Prof. Sulaiman.
Okay, thank you.
Tolong bawa dulu ke ruang konsultasi. Habis itu makan sama.
Ini caranya kan kita misalnya udah how to make it like into some kan berasa banget pasti dalam tahap yang apa
Iya, buat device sih.
harus ada device.
Iya, kan Mbak Dika misalnya. Mbak Dika sudah ada SPE-nya kan, ada tambahan apa kayak gitu. Mungkin itu ada device di sini.